Good afternoon, everyone. It's my privilege to chair the in-water cleaning session. It's not a very complicated subject, so this is going to be a pretty lightweight afternoon. I will remind the speakers that I am session chairing tomorrow, so if they do want to say anything, just note that I will have the last say. The first speaker I want to introduce is Mario Tamburri, and he's going to be talking about independent performance evaluation. So thanks, Mario.
Well, thank you. It's a pleasure to be back here to speak with you again. I was here 2 years ago introducing an idea, a project that we had on evaluating in-water cleaning systems, and I'm glad to be able to have a chance to report back out what we've done over the last couple of years and tell you about some of our plans moving forward. While this is a talk around an evaluation of a particular system, really the overarching goals of this project is to help facilitate the development and adoption of these new innovations that can help solve a couple of problems, help solve a ship operational need, as well as biosecurity needs that we've all been talking about last few days. Underneath all of that, though, we also want to be able to provide some of the fundamental science needed as regulations start moving forward. And we also want to help sort of develop protocols for how this sort of testing and evaluation of these systems moves in the future. So that's sort of the reason why we're moving down this path. The other thing I want to mention is that while we're going to be talking a little bit about a particular system that we tested, really the goal of my talk today is to talk more about the protocols, the methods that we're using and we're evolving, and not as much of the individual performance of that one system. My co-authors are listed here. It's a broader effort with lots of people, and I'll show you a list of all of our collaborators and so on at the end. So just for some quick background, but we've heard about all this stuff the last few days. But the way I kind of think about the issue of vessel biofouling is from two perspectives, right? There's one side is the vessel operational issues, and of course we've heard all about how biofouling increases roughness and drag and fuel consumption and air emissions and so on. And it's not just the outer surface, of course, of the vessels. There's the inner piping systems and the like. And so the way that the shipping industry, as we've talked, has been tackling that problem, that operational problem, is through a whole husbandry approach that includes anti-fouling coatings, whether they're biocidal or they're non-stick fouling release type coatings, and in-water cleaning. And in-water cleaning can be traditional divers with brushes and scrapers all the way to these new innovations we're talking about today. When you think about it from the other side, though, there's, of course, a biosecurity issue around vessel biofouling. I put this one graph up, not for everybody to try to straight and see what those numbers look like, but this is just one of the examples that illustrates how important biofouling is as a vector for invasive species. This is some work by Greg Ruiz, one of our partners on this effort, and it just shows that when you compare it to other vectors, biofouling appears to be the most important, even compared to ballast water and other ways these organisms move around the world. So because of that problem, we've been hearing a lot about these regulations that are evolving and how over the past few years this has really picked up some momentum. These are important regulations. We do need to protect the environment and prevent invasive species. But to make these regulations happen, to make these rules successful, we are relying on new innovations to help solve the problem. So when it comes to in-water cleaning technologies or approaches, there's a sort of continuum of different types, and I think Chris will be talking a little bit more about this in a little while, so I won't go in too much depth on this. But on one end of the spectrum, you can have things like in-water cleaning to remove biofouling, clean and sort of capture approach. And on the other end of the spectrum, you can have a proactive, preventive way of dealing with it by periodically, proactively removing biofilms that will then in turn minimize macrofouling growth. And a couple of these cartoons are taken from Chris and Eugene's paper that they sort of illustrate that. That top one is what you would call maybe a clean and capture type system where you have a cleaning unit, and in this case a diver-driven unit. It mows the lawn, if you will, of macrofouling. That material is captured, brought to shore or to a barge. It's treated, usually filtration, and waste is removed and disposed of, and clean water goes back to the environment. So that's sort of one end. The other end would be just a cleaning unit that's perhaps robotic by itself, but it will proactively remove slime layers from the ship. What we're trying to do is ask sort of three fundamental questions about these types of systems. And one is how well do they clean? And the other is how well do they reduce the biosecurity risks? And how well do they reduce the water quality risks? And so a lot of our protocols are really based on those fundamental questions. And our protocols are also based in large part off the initial work done by Morrissey et al. On the paper in 2015, I believe. But what we're able to do is we have a couple of programs that have been working on independent testing of technologies over the years. One is called the Alliance for Coastal Technologies, or ACT. It's been around for about 20 years, and we focus a lot on things like sensors and sensor platforms for studying and monitoring aquatic environments. I have another program called the Maritime Environmental Resource Center, or MERC. It has a similar sort of structure, but it's been mostly focused on green ship, green port sort of technologies. We've been heavily involved in the ballast water management system world, testing the systems for certification by the U.S. Coast Guard and other administrations. So with the expertise of those two independent testing organizations and a variety of partners you see listed there in the logos, we put together this team to tackle independent testing of water cleaning systems. What we did is about 2 years ago or so is released a public call. It was right after, I think, the meeting here a couple years ago. And we asked for anybody who's developing or operating an in-water cleaning system that would like to participate free of charge in water cleaning testing through our programs. We didn't charge any, or not charging any of the vendors for this activity. However, of course, there is a cost associated with participating, getting your gear around, your people around, and so on. We actually got 8 different applications by 7 different companies shown here. And we ended up working for our first set of tests, and I'll show you today, with the SGS whale shark, and that's that picture there next to the Cape Orlando in Alameda, California, and that's their gear set up and our testing system sort of set up. So the data and some of the conclusions we draw is from that set of tests. Where we are trying to move forward on a series of tests looking at more of the proactive prevention sort of approaches, often referred to as grooming, with a couple of different companies. We're hoping to get off the ground earlier this year, but I think we are going to be able to do some of that testing very soon. So this is just a very simplified graph of the detailed protocol. I don't have time to go into all the details, but our protocols are publicly available. They were vetted by a technical advisory committee. We worked with individual vendors on their suggestions and so on. But in gross overview, what we have is a protocol that looks at the biofouling removal efficacy. And that's through a series of dives on control and treated sites on vessels. We had 2 different vessels for this test. One was the nuclear ship Savannah in Baltimore. That vessel was decommissioned and his coating is about 10 years old. She was very heavily fouled and a good challenge. The other was the Orlando I showed you earlier in Alameda, California. The dive surveys did a variety of randomized plots in the control and treated areas, on vertical sides, flat bottoms, and there's a quadrat sort of system shown there on how the divers were collecting data. We collected data both on macrofouling, organisms greater than 5 millimeters or so, and biofilms as well. We did not distinguish between live and dead. We did that intentionally because, first of all, we learned some valuable lessons in the ballast water world when it comes to live and viable and dead and the complications associated with that. But also because when it comes to the ship operations side, it doesn't really matter if the barnacle's alive or not. The roughness is the roughness. So we assumed everything, in quotes, was alive, and that's, in fact, a safer way to, like a conservative way to look at this from a biosecurity perspective as well. We looked at capture and retention of efficacy of these systems. How good are they at collecting the material that they're removing from the side? We did this through a series of dive studies and sampling that's shown here. And we looked at the treatment efficacy. That's the box on shore, if you will. So we have a series of water samples set up looking at copper, zinc, because of the coatings that are on these particular vessels. We looked at total suspended solids, particle size distributions, and a variety of other environmental factors. Those samples were taken some of them were taken the day before, hour before cleaning events, after a cleaning event, to capture background environmental variability in those and parameters. but also during the cleaning event itself through a time-integrated continuous sample at those different points shown on the top figure there. So we sampled very far away from the cleaning event continuously, really close to the cleaning activity continuously during the cleaning, and then actually from the cleaning unit itself, which you would suspect to have the highest signal if there was going to be one, before and after their treatment system on shore. Here are just some images to help explain that sort of setup as well. That one image is a Google Earth shot of the savannah in Baltimore, and the green dots are the pre-samples and post-samples, just capture copper levels as it fluctuates naturally. Well, naturally, it fluctuates in Baltimore. The yellow dots are the continuous samples were taken during the cleaning event. You can see the sort of cleaning area there as well. There's a picture on top there. The divers getting ready to bring their transect down below and take some randomized samples of the control and treated sides of the ship. Water sampling at discrete locations, and then continuous sampling on shore there. So this is only one data slide I'm going to show you today, just to give you a feel for the sort of information we gathered. The full report on this is publicly available, as is the protocols I mentioned earlier, and they're available on our website. Our goal is, again, not to emphasize the performance of one system. It's more to talk about how testing can be done. But these figures show you the biofouling removal efficacy. The one with just the limited number of bars on the left side, I guess there, is on the Savannah, the first vessel. We weren't able to do the flat bottoms on that vessel as we had planned. The other ones is for the Orlando, where we have flat bottoms and vertical sides. The bottom line here is that the control and areas stayed fouled. They were fouled and they stayed fouled. The treated areas were cleaned dramatically. The removal rate was quite high. The pictures below are just a shot of the Orlando before the cleaning event and a similar location on the ship after the cleaning event. So you can see how much material was removed. So after this set of tests, and we have a lot of information on the copper levels and all those sorts of things, but after this series of tests, what we decided to do is bring together a bunch of our colleagues and experts around the world to look over the results, discuss some of the lessons learned from that first set of trials, and to sort of think about where we should go in sort of standardizing or harmonizing testing of these systems. It's a complex issue. There's a few of us around the world trying to do this sort of work, and we're all going to benefit by trying to do this in a standardized, a similar way as much as possible. So we had 24 folks from around the world. We went to lovely Honolulu in April. It was a very nice workshop. You can see some of the folks there, and some of you can see yourselves in the picture in the room today. Our goals were to develop an understanding about the current state of the science around testing these systems, and to, again, look at our lessons learned from that first set of trials, what are the challenges and what's feasible. And ultimately, what we wanted to get out of this is to help build some consensus on how do we do a rigorous, comprehensive, scientifically sound, transparent set of tests on these systems that will help them mature, help them move into operations, and help address the needs of industry and biosecurity and water quality. So what I'm going to talk about in the last few minutes is just some of those recommendations and lessons learned moving forward. First, the good news. We all concluded that, yes, in fact, you can do this. There's nothing there that's insurmountable. So rigorous independent testing and standardized evaluations is very much something that we can all do. And that's good. So we can put some hard numbers and some good science behind the performance of these systems. We agreed that standardized protocols is going to be important, and this is really important in the future when we start thinking about certifications or approvals or acceptance of these sort of systems. You need to be able to compare how they worked, and these systems shouldn't need to be tested in every location around the world. So the standardization is important. What we also concluded from these first rounds of tests is that the current systems in general perhaps that we tested are doing a pretty good job at the operational needs of the vessel, and that is removing the macro fouling. When it comes to other issues like water quality or others, they probably need some maturation there. If you look at the report of this one system we tested, the copper levels on discharge were relatively high. They've since made adjustments to their system to address that with media that removes metals. But they're learning, as we all are, as we go forward in this area. Another thing that was clear is that the systems that are evolving now are really driven by the operational needs of the ships. So they're really focused on the main hull surface of the vessels to reduce drag. There's not a lot of attention at this point on the niche areas, and as we all know from the biosecurity side, that's probably the hot spots. It's not that these systems can't be adapted for that. It's not that it's technologically impossible. It's just there's really no market for that, if you will, right now. However, as regulations around biosecurity and fouling start evolving, I think they'll quickly adapt to address that as well. So our test didn't look at niche areas because the vendor said they don't do niche areas. Another thing we talked about is a need for some uniforming our terminology around these systems. I'm not going to even address that at all now. I'll hand it off to Chris for later because it's complicated, but maybe he has a solution for us. We also didn't look explicitly at impacts to the coatings or into internal piping systems, water systems of the ships, where of course can be fouled as well. This evaluation didn't include either of those two aspects. Fortunately, there are other groups looking at those. We were able to document visual observations of scuff marks and so on the vessel from a cleaning event, but the true impacts to coatings needs to be addressed in a more formalized and explicit way, and maybe Eric's talk this afternoon will address some of that as well. Another thing we concluded, I think, from the workshop in particular was that the unit of replication, if you will, on these sorts of tests really should be the individual ship that you're testing these systems on. And that's similar to the approach in the ballast water world, where an individual ship voyage, you can run a test, but not the individual ballast tanks on the ship wouldn't be replication. So what we're recommending here in the future is that you at least do 3 different ships to see how broadly applicable these systems are. If possible, and it's not easy, especially in these early days, different types of ships with different types of coatings, different types of fouling, et cetera, would be great to capture. Again, it might work really well in one situation and not in others, and there's a lot of variables that can impact that performance, and I'll show you a slide on that next. Another thing we learned, I think that was really important and really valuable, is that you can run some of these biofouling surveys, capturing fouling on the side of the ship, even under low visibility conditions. Morrissey et al. Recommended at least 2 meters of visibility, and that's outstanding. We'd love to be able to work in that all the time, but the reality is you're often in locations where it's going to be much less than that. In particular, the Baltimore test, it was chocolate milk. We had maybe 6 or 7 inches of visibility, but we were able to still capture some really robust data on the fouling through the diver observations on that grid transect I showed you. So that's encouraging that even under harder conditions, you can still pull off some of these tests, and that approach is applicable to the niche areas as well. Now that said, documentation with videos and with images, still images, is still really important, so that needs to be part of this and not excluded. And then, sampling of water quality has to be thought about carefully. You want to make sure we capture the environmental variability of the parameters of interest, because there are levels of these biocides in the waters already. You want to sample in a way that you know what the range is, and so if you get a reading from a sample during a cleaning event, is it exceeding that normal range or is it within that normal range? So thinking about that carefully is important. Of course, you want to focus on the different biocides that are in the coatings, but we're also, I'll talk about later today, recommending looking at microplastics, so stay tuned for that. So I mentioned the different variables that are important when it comes to operating in water cleaning systems as well as testing these different systems. And this is something we spent some time with at the workshop. There's lots of different things that can have an impact, from the vessel operation size, the type of vessel, the age of the coatings, the fouling that's already there. All that will make a difference on how the in-water cleaning operates and how we run the tests. Environment's the same way. Currents, water clarity, wind, background levels of different biocides, all that sort of stuff will have an impact on how the tests are run and how the system performs. The in-water cleaning systems themselves can be configured in lots of different ways under different situations. what types of brushes or water jets, how they operate it. Do they do a single pass, double pass, overlaps? All that stuff makes a difference. The operators themselves, there's some variability. If it's an ROV pilot or a diver, how experienced are they, right? All that has an impact. Now, we're not going to capture all that variability in a reasonable set of tests, but we need to keep all of that in mind when we're looking at these and evaluating these systems, and try to capture as much of that variability as possible. So just a quick slide on where we're going next over the next few years. As we're taking the results from that first test and some of these recommendations from the workshop, and we're putting together a publication. A few of us already met the last few days here about the paper. Our goal is to try to get this submitted by the end of the year that describes a lot of this in much more detail. We're trying to get our in-water cleaning prevention proactive approach testing done sometime soon. And that's, again, looking at removal of that soft biofilm to prevent macrofouling growth. The issue with that sort of test is that, unlike in-water cleaning capture, where you can do it before and after, when you're looking at those prevention systems, you need to follow that vessel through time, right? So if it proactively grooms, if you will, the vessel every 3 weeks, well, you need to sort of follow that ship for 9 months to a year to see if there's a difference in macrofouling growth. One thing I hope we can get started on next year is looking at these same sorts of tests when it comes to the traditional diver manual sort of biofouling removal. This is happening everywhere now. It's happening all over the world. I was told by a ship operator that 95% of the world's fleets is cleaned by these sort of manual approaches that really don't look at capture very much. If we're going to evaluate these new innovations that do all this fancy stuff, including capture, we should have a look at what we're doing now and to see how they compare when it comes to things like environmental safety and biosecurity. We're still interested in looking at offshore platforms and in-water cleaning and an approach that might solve some of those problems. And we're going to go through a series of these evaluations over the years, hopefully, again, to help these new innovations mature and help all of us understand how well they work and how they might solve our problems. And I'll just end here with acknowledgements of the team. It's a complicated effort, so there's lots of experts on this. The tested team is shown there with sort of the PIs from our different groups, but there's lots of technical help underneath there. There are lots of technicians and analysts and QA, QC personnel and the like. We have a technical advisory committee listed there. They help guide this project. They are acting as peer review of our reports and that sort of thing. And a lot of these experts make sure we're doing things the right way. And then our funders are also listed there. So I know I'm a little bit over time, so I'll just stop there and thank you for listening.